So we're beginning a new unit. We're beginning Unit 7. We are doing anti-differentiation, which is going to be our big word this semester, or integrals or integration, however you want to see that. Today specifically, we're going to talk about rules of integration, and more specifically, we're going to talk about one rule, our power rule. But before we get there, let's go ahead and backtrack a little to explore how we got to where we're going to get to. So let's approach this function, f of t equals 2t minus t. Well, first things first, we're going to ask us to sketch this graph. What kind of graph is this? What kind of parent function is this? It's a linear line, right? With a y-intercept of -2 and a positive slope of 2. And so that gives us this handy-dandy line right here. And because of this, now we can approach some definite integral questions. So let's look at those questions. So let's assume that a of x, some function, big A of x, is going to be equal to our definite integral from 0 to that value x of f of t dt. Well, first of all, this x value, whatever x value I place here, is going to have to go right here according to this function. So let's use this graph to figure out some of these questions. Question 1, we're going to look at a of 0. So I went from 0 to 0. Did I move anywhere? If I go from 0 to 0, have I created any line to create a shape above or below in my function? No, not at all. So if I haven't gone anywhere, I haven't created area, therefore my answer has to be simply 0. This is actually a property of integration. It's our 0 property. We saw that in Unit 6, but we're gonna remind you today. So our second question says from a of 1. So from 0 to 1, do we create any sort of shape? 0 to 1, absolutely. First things first, we want to identify what that shape is. This is a problem with some of you guys, is, some of you might think this is the space we're looking at, but that's not bounded by my function and my x-axis. Or you might think this is the space we're looking at, but again, it's not bounded by my, right here. It's not bounded by my function and the x-axis. You have to look between those. So here's my x-axis, here's my function. I draw this handy-dandy shape, and it's a triangle. In fact, it's a right triangle, so I get to use my base times height over 2 equation. My base is 1, my height is 2. That gives me 2. 2 over 2 just gives me 1. So my answer for this area is 1, but I'm not quite done, because where is my shape? Well, it's below my x-axis, therefore I have to make my area negative, so my answer is actually -1. Okay? Let's move on to our second value, so a of 2. So I go from 0 to 2. So we go from 0 to 1, we already know what shape that is, that's our little triangle. 0 to 2, here's my x-axis, here's my function line, and I bound it and I create my shape. Well, it's a triangle. In fact, is it not the same size triangle as this space right here? It actually is, so I know that it's an area of 1. If I wanted to double check that, I could. Base of 1, height of 2, 2 over 2 is just 1. It's absolutely correct. So I know that this area right here is 1, but that's not quite the answer we're looking for. We're actually looking from 0 to 2, so I have to add these together. So -1 plus +1 just gives me 0. They cancel out. This is our net area. So I have a net area of 0. Continuing on, we look at a of 3. So now I go from 0 to 3. So I'm just going to tack on one more shape right here. And because this is a simple graph, I'm just going to count my squares. So 1, 2, that's an area of 2. And then I have another triangle that matches these triangles, so that's an area of 3. So if I go from 0 to 3, I'm looking at the total. So -1 plus +1 plus +3 gives me an answer of 3. And yes, I could have seen this as one giant triangle, absolutely. We could have done that. And in this case, because we're just building off of each other, it's just easier to look at simple shapes. So our next one is going to be a of 4. So we're going from 0 to 4. Again, I add on that little bitty shape. And if I look at that, I can see I have 1, 2, 3, 4 blocks and one triangle, so it has an area of 5. So if I go from 0 to 4, I have to look at all of my areas. So -1 plus +1 plus +3 plus +5 gives me +8. Okay? At this point, this is just a review of definite integrals or area under the curve, but we're going to talk about one more little property real quick. What happens when we go from 0 to -1? Well, first things first, let's identify that shape. Okay, so from 0 to -1, here's my x-axis. Oops. here's my x-axis, here's my function, and I shade in between. And so if I look at that, I have 2 blocks and 1 triangle. So that's an area of 3, but I have to remind myself, where am I? I'm under the x-axis. So right now, this is an area of -3. However, where am I going? I'm going from 0 to -1. In our previous examples, we went from 0 and we went right on our x-axis, or we went positively on the number line. Here we're going backwards. We're going negatively down the number line. So when we go backwards, we have to flip the sign. So my area of -3 now becomes +3. What happens if we keep going? What if we say from 0 to -2? Well, it's the same concept. 1, 2, 3, 4, and a triangle of 1, so 5. So I have 3 and 5, total area of 8. It's under my x-axis, so it's a total area of -8, but I'm going backwards, so I change the sign, and it becomes +8. It's here, you can't quite see it, sorry about that. Let's move forward, a little bit more exploration. Let's think of all of these as coordinate points, and let's just go ahead and plot. Well, how do I see my coordinate point? I know what you're saying. You're saying, Ms. Jag, these are just numbers. I don't see coordinate points. Well, is this my x-axis? I mean my x-coordinate point, my x value, sorry. Well, absolutely, and this will be my y value. So I've got a coordinate point at 0, 0. 1, -1, 2, 0, and so on and so forth. So if I go ahead and plot those, that becomes 0, 1, -1, 2, 0, 3, 3, 4, 8. I'll leave myself a space for 8, that's okay. And now you can see as I've plotted these coordinate points, I've created some sort of shape. What shape do we think that looks like? It's absolutely my quadratic curve. It's my x squared. So what happened? What is this pattern that we've just created? Let's do a little bit more exploration on that pattern. And to do that, we're going to actually go to our calculator. So I'm going to switch over to my calculator real quick. We use the TI Inspires. So I'm going to go to my graph. And what I'm going to do is I'm going to look at my definite integral graph. So I use this math button, which is the button to the right of 9. I get a pop-up menu and I click on my definite integral. And I'm going to go from 0 to x of my linear line, which was 2x minus 2, I think. And we have with respect to our variable. And boom, we don't just get any old quadratic function, we actually get the quadratic curve that we just plotted those coordinate points for. Don't they match up? Absolutely. And in fact, if we wanted to continue this exploration, oh, I went too far. If we wanted to continue this exploration even further, I'm going to go ahead and look at one more line. So we're going to look at x squared minus 2x. So I'm just graphing another line. This is x squared minus 2x, and we're going to see what that looks like. And in fact, that x squared minus 2x created a quadratic curve. We should have been able to predict that because it's x squared is my highest power. But it didn't just create any old quadratic curve. It created a quadratic curve directly on top of my previous integrated linear line. Well, why did it do that? I'm going to skip through these slides real quick. Why, when we look at x squared minus 2x, does it give us the exact same quadratic curve? Well, this is that relationship that we talk about with our derivatives kind of knocking down a peg and our integrals kicking it up a notch. So when we think about our derivatives, we think that if we have an x to the 4th function, when we take a derivative, we knock it down so it becomes cubic. Our cubic then becomes quadratic when we take the derivative. Our quadratic then becomes a linear becomes some sort of constant line, and from there the only value left is 0. Well, my integrals go backwards, so or upwards, or however you want to see that. So my 2x minus 2, my original linear line that we've been working with, my linear line should go up and it should become quadratic. And in fact, this is the exact integral of 2x minus 2. That's why it looked exactly the same. So my linear became quadratic, as we saw. My quadratic would become cubic. If I integrate cubic, it would become x to the 4th, and so on and so forth. Oh, using that information, well, what can we conclude? we can conclude this huge statement. But like usual, I don't ask you guys to memorize this and really be able to speak of f prime versus, no, I want you to understand the concept. So the concept is saying, if my big letter f, in this instance, my big letter f is my antiderivative or my integral, if my big letter f is my integral, if I take the derivative of that integral, I should reach my original function. And we see that. So let's see that a few different ways, backwards and forwards. So if I have if I know, I'm sorry about that. If I know x cubed, that's really thick. Okay, there we go. If I know x cubed, what is the derivative of x cubed? Well, we know that. We bring our exponent to the front. We subtract 1 from the exponent. So we know that this is going to be equal to 3x squared. Well, the same is said the other way around. The integral of 3x squared dx is going to be equal to x cubed. And that's what we're going to prove today. And all we're saying in this statement is that they work forwards and they work backwards. My derivative of a function is, the derivative of my integral is going to equal the function. The integral of the function is going to equal my integral, obviously. Okay, so let's actually work on a sample problem. In order to do this sample problem, what we're going to do is explore 3 variations of the same function. So we're going to look at f1, f2, and f3. I'm going to go ahead and start with our f1, f2, and I want you to see if you can develop a pattern based off of what I'm saying. So we're going to still use that 3x squared that we were using previously. I already told you that the integral of 3x squared is x cubed, but let me prove it to you. So if I have, we need to know some f1, f2, or f3 function whose derivative is 3x squared. So we're going to declare f1 as x cubed. And again, we'll prove that in just a little bit, but x cubed, is this a true statement? Absolutely, but I'm going to change it up very, very quickly. Let's say it's x cubed plus 12. Well, is this still a true statement? Well, the derivative of x cubed is 3x squared. That's true. But what's the derivative of plus 12? Well, we know that the derivative of any constant is 0. So is this still a true statement? Absolutely. The derivative of this is going to equal 3x squared. Let me write down an f2. X cubed, let's say minus 76. Is this still a true statement? The derivative of x cubed is still 3x squared. The derivative of negative 76 is the derivative of a constant, which is just 0. So this is still a true statement. Do we see a pattern developing? No matter what I put down, I could put down plus 1. Doesn't matter. It doesn't matter what that value is. I can put down anything and this will still be a true statement because the derivative of any constant is going to be 0. Well, why did we develop this pattern? It's to prove this, that x cubed plus c. That's what we want to see on all of our integrals. And why do we do this? Well, this is called a constant of integration. It is an arbitrary constant, but it is not an arbitrary concept. So please, please, please tack on plus c to all of your integrals. There are only 2 exceptions. One exception is the definite integral. If it is defined from a to b, then we don't need plus c because you're searching for a specific area under the curve. But if it's an indefinite integral, we don't know where it starts, we don't know where it ends, then we need to tack on this plus c. My only other exception to this rule is when we're solving for c. We're not there yet, so you don't have to worry about it right now, but when we solve for c, then obviously you're not going to tack on plus c, you're going to actually put what the constant value is. Okay, so let's actually look at a true example of our integration property. At this point, I've just told you the integral, but let's learn how to do it. So what we're going to play with today is our power rule, which is rule number 3 on that second page in your packet, but it's here for you in case you've forgotten. It's my indefinite integral of x to the nth dx, so n is my exponent. So all I'm going to do, very simply, very basically, step 1, I'm going to add 1 to my exponent. Step 2, I'm going to divide the whole thing, so all over my new exponent, or n plus 1. It's that simple. But of course I can't forget to tack on, always, always, always tack on plus c. So let's explore a very simple problem. We're going to do the definite integral from x to the 4th dx. So my n is my exponent, so my n is 4. So first step, I tack on plus 1. Second step, all over my new exponent. Okay, so now I just combine these, do a basic arithmetic, x to the 5th over 5. Am I done? Well, not quite. I always need to tack on plus c. So this becomes plus c. Is that my answer? Well, we could verify, couldn't we? We know how to take a derivative. So x to the 5th, I bring this forward, that becomes 5x to the 4th over 5. My 5's cancel out. That means I'm just left with x to the 4th, which was my original function value. So this tells me I did integrate correctly. Okay. I wanted to double check my work. I always put my answers at the bottom. There it is. Ta-da. We did do it correctly. So let's look at another example. But before we continue on to these examples, today's lesson isn't going to be difficult with the calculus. Today's lesson, you guys face some problems with the algebra. So let's do a tiny bit of algebra review. So what do I know? The square root of x can be rewritten as an exponent fraction form. Well, my square root is my most basic root, so it's base of 2. So I know I have a root value of 2. So that means my root goes in the bottom of my fraction, my power goes in the top of my fraction, my numerator. So it's the same as saying x to the 1/2. Using that same concept, what if I had x to the 9/5? How would I rewrite this to make it more appealing to the eye, to go backwards basically? Well, my 9 is my power, my 5 is my root, so this is the same as saying the 5th root of x to the 9th. Well, you might be saying, Miss Jag, why do we have to know forward and backwards? Well, I have to know how to get rid of a root in order to apply my power rule. I have to see it in a form I can use. And then at the end, I have to know how to transform it back, because if we're solving, this is an easier form to solve than this. Just simply. You can't solve it this way, of course, but this is visually easier to understand. What happens if I have some value below? If I have x cubed below, well, at this point, we haven't learned what to do when we divide an integral. All we've learned about all we're going to learn is the power rule, so we want to bring it to the numerator. We don't want anything in the denominator. Well, how do I do that? I have to change the sign of my exponent. So this x cubed, to bring it up, has to become x to the -3. So now I can get rid of it. Okay? But what happens if there's stuff in the numerator? Well, I'm going to multiply it. That's all I'm going to do. But if it's multiple things, I have to remember to place them in parentheses so that I can distribute. And of course, if we are multiplying exponents, we're actually adding those two exponents. So this answer would be 2 plus -3 is actually x to the -1st. And then this technical exponent is 1, so 1 plus -3 gives me x to the -2. And now this is in a form where I could apply a power rule. My final bit of algebra review would be what do I do when I have a fraction on bottom? So if I have a over b all over c over d, this is the same as saying a over b times the reciprocal of my denominator. Now this seems simplistic, but today we're actually going to see a few problems like this. In fact, we're going to see it more in the form of something on top divided by some sort of fraction. So the simplest way I can tell you to get rid of this is flip your denominator and drag it to the front. So all I'm going to do is flip this, so it's now 3 over 2, and I'm going to bring it to the front, so it's 3x squared over 2. It's a simpler form. If I plugged in any value now for my x, it would be easier for me to calculate that arithmetically versus seeing it like this. I mean, either way is solvable, but this is a easier method to see visually. All right, let's actually continue on with our example problem number 1. So we're going to do x to the 4/5. The very first thing we want to do is evaluate, do we need to do any algebra? Well, in this instance, we don't. We don't have any roots to deal with. We don't have any denominators. So we can just go ahead and get started with our power rule. I like to rewrite all of my fractions in true fraction format, where a numerator on bottom and a denominator on, numerator on top, denominator on bottom. I don't like it with those diagonal slashes simply because, again, I stress that visually, that is more difficult to play with. Not in this particular example, but later when you have 7 or 8 variables, or you're dealing with multiple steps, sometimes that diagonal slash gets lost in the fray. So I like to always rewrite it like this. Again, it's your preference, this is your math, but it's your decision. So step 1, I'm going to add 1 to my exponent, but I don't want to add 1 in the form of 1 because we have a fraction. I actually want to add 1 in the form of my denominator, which is 5. So I'm going to add 1 as 5 over 5. Step 2, I divide the whole thing. Oh, let me color code, hold on. Okay. Step 2, I'm going to divide the whole thing by my new exponent. So this becomes 4/5 plus 5 over 5. Well, that's pretty simple math, right? 4 and 5 is 9. And I just go from there. So that becomes x to the 9/5 all over 9/5. Here's that fraction on bottom I was talking about. So I'm just going to flip it, drag it to the front, and that becomes 5x to the 9/5 over 9. I want to do something about this variable because I don't want to see at the end, I don't want to see an exponent in fraction form, and I don't want to see an exponent with a negative, simply because, as I said, if you're plugging in values, you want to make it easier for yourself to see. You want to be able to see that it's just saying the square root of 9 instead of seeing 9 to the 1/2 and having a small brain fart or something. So that's why I just ask you guys to practice changing it over, simply because in the future we may be plugging in values. So this actually becomes the 5th root of x to the 9th. So the 5th root of x to the 9th all over 9. Am I done? Not quite. What do I have to tack on to every integral? Plus c. So now am I done? If I want to double check my work, I can see my answer right here. 5/9 x to the 9/5 plus c is absolutely correct. You might be saying, well, why did we not just leave it like this? Again, I remind you, I just want you guys to practice changing this over for when you need to actually evaluate a value instead of leaving it as x. Let's continue on to example number 2. So if we do the cubed root of x, then I want to change my cubed root. So this is algebra. We want to change the cubed root of x to x to the 1/3. From here, we can actually apply our power rule directly. There's no other algebra we have to do. So step 1, I add 1 to my exponent. Step 2, it goes all over my new exponent. So this now becomes x to the 4/3 all over 4 over 3. I flip it, drag it to the front. This becomes 3x to the 4/3 over 4. I get rid of this x to the 4/3. This becomes 3 cubed root of x to the 4th over 4 plus c. Was I correct in my reasoning? Yay, I was. Absolutely fantastic. Let's continue on. Okay, so now here we have something in the denominator. We also have a root, so we got to do a little bit of algebra manipulation. So what I'm going to do to make my life so much simpler is I'm going to drag out that 4 by making it a coefficient, because my value up top is technically 1, so it's actually a coefficient of 1/4. So it's going to become the integral of 1/4 times the square root of x dx. This is also a property of integration that we kind of saw, we definitely saw it in derivatives. It's called the constant multiple, where we could take that constant that was attached to the front and drag it outside of our derivative. We can do the exact same thing with integration. This is the same as saying 1/4 times the integral of the square root of x dx. So I have two methods. It doesn't matter which way I solve it. I can leave my 1/4 in, or I can leave my 1/4 to the outside. Doesn't matter. So we'll explore both ways. So let's go ahead and do it with my 1/4 on the outside. So if my 1/4 is on the outside, then I'm just going to leave it there. So I'm going to say 1/4 times the entire quantity of my integration. So first of all, we rewrite that square root of x as x to the 1/2. Then I apply my power rule. First step, plus 1 to the exponent. So I have plus 2/2 all over my new exponent. So 1/2 plus 2/2. And then this simply becomes 1/4 times x to the 3/2 over 3/2. I flip my reciprocal. So here I have two choices. I can flip it and immediately multiply, or I can leave it for a second. So we're going to see it that way. So 1/4 times 2. I'm going to go ahead and change this. So this is the square root of x cubed over 3. I can simplify, so 2 goes away. This just becomes 2. That's 1/6. So my end answer is going to be 1/6 of the square root of x cubed plus c. Or we could have seen that as the square root of x cubed over 6 plus c. It's either way. We can double check our work. Ta-da! Fantastic. We get to example 4, and now we have something a little bit different. In our denominator isn't some constant value, so I can't just rip it out front with as a coefficient. It's actually our variable. So how do I change that? I have to do something to the exponent. I have to change that exponent. And what do I change it to? Drag it up or to drag it down? I make it negative. So this now becomes, instead of the integral of 3t over 3 over t4, it becomes 3 times t to the -4th dt. Again, I can pull this 3 outside. We did that last time. This time I'm going to go ahead and leave it in so you can see how that works. So if I was going to integrate that, I'm just going to bring that value right here, make it a little easier for me. If it's short, I can't reach that high. The first step we want to do is add 1 to our exponent. So we do plus 1 all over my new exponent. This becomes 3t to the -3 all over -3. Hey, guess what? I can simplify right there. I can cancel out my 3's. But I want to make note, do not cancel your negative. This was not a -3 up top, so it's not going to cancel the negative. I have to drag this negative back up top. So my answer is going to be -t to the -3 plus c. But again, I told you we don't like negative exponents because visually we can't see that as simply as we would see the same equivalent, which is -1 over t cubed plus c. They're both correct answers, but if I had to plug in a value, if I asked you to solve this for 3, t equals 3, if you looked at 3 to the -3, would you be able to understand that as the same as 1 over 3 cubed? Some of us can, some of us can't, so that's why I asked you guys to practice switching it over. I want to double check my work. There it is, -1 over t cubed plus c. Fantastic. All right, here's another problem where I got to do a little bit of algebra manipulation at the front. So we're going to take, we'll say that the integral now becomes t to the 5th times, so my square root of t on bottom becomes t to the 1/2. To bring it up top, I change my 1/2 to -1/2, so it becomes t to the -1/2. If I multiply these, I have to add my exponents. So 5 plus -1/2 is the same as saying 5 minus 1/2. We're going to do that in fraction form, so you're actually going to end up with 4 1/2, which is 9/9. So we're looking at the integral of t to the 9/2, and now we can actually get started. So step 1, we're going to add 1 in the form of 2 over 2 all over our new exponent. This now becomes t to the 11/2 all over 11/2. I flip this, drag it to the front. That becomes 2. Let's go ahead and change this. This is t to the 11th, and this is my square root, so it becomes square root of t to the 11th over 11 plus c. Is that correct? It sure is. Now we're going to look at example 6. So examples 6 through 10 are a little bit harder, not because of the calculus, but again, because of the algebra. So here we have to look at this, and we have to take that x to the 4th and bring it to the top. Well, how do I do that? I make the 4 negative, so if I bring it to the top, it's going to be x to the negative 4th. But I have a whole bunch of stuff in my numerator, so I have to put it in parentheses and distribute my value across. So this is going to be x squared plus 2x minus 3 times x to the negative 4th. When I multiply my exponents, I'm actually adding them, so this is now going to be x to the negative 2 plus 2, this is 1, so negative 3 minus 3x to the negative 4th dx. And now I can continue on. But I'm sure some of you saying, well, Miss Jag, now I don't know what to do because it's the first time we've had operators in between. And that's true, but go back to derivatives. Think about our sum and difference rule, where we could take some, let's say I was taking the derivative of sine x plus cosine x. That was the same as saying the derivative of sine x plus the derivative of cosine x. Ooh, that's terrible handwriting. But it was the same. We could take that plus and we could split it apart and say it was two different derivatives. We did do that. Well, guess what? With integration, we can do the exact same thing. So I could see it as an integral of this, an integral of this, and an integral of this. Or we can do one giant formula. So I'm going to do one giant formula because that's what I like to do. So I'm going to leave myself some space. So we're going to do x to the negative 2 plus 2x to the negative 3 minus 3x to the negative 4. We're going to apply our power rule, so we're going to add 1 to our exponents. I have no idea why I said that. Divide the whole thing by the new exponent. Okay, and so if I solve through with that, negative 2 and 1 is going to give me negative 1 over negative 1. And if it's over negative 1, then that means there's nothing really I'm over, it's just negative. So this becomes negative x to the negative 1. This becomes negative 2. If this is negative 2, so let's explore that. If this is negative 2, then my 2's cancel, but my negative stays. So this now turns into minus x to the negative 2. Okay, this becomes negative 3, but here my two negatives do cancel because I have a negative up top. So this becomes plus, oops, I don't need a 3, they canceled, x to the negative 3. And again, we need plus c. This is one answer. A second answer would be getting rid of my negative exponents. So it should be negative 1 over x minus 1 over x squared plus 1 over x cubed plus c. Okay? And if I wanted to double check my work, I could see that we have that exact value for our answer. Let's move on to example number 7. So here we have more algebraic manipulation. So we're going to get rid of our roots by turning it into x to the 1/2. We're going to bring this second new denominator value to the top. And so what that's going to look like is my integral of x to the 1/2 plus, and I'm going to bring that 1/2 to my coefficient, 1/2 times x to the negative 1/2 dx. Now here we're actually going to do a sum and difference so that you can see what that would look like. This would be the same as saying the integral of x to the 1/2 plus 1/2 times the integral of x to the negative 1/2. I forgot my dx's, sorry. Okay, so let's go ahead and work this problem slowly. So we're going to do our first value is going to be x to the 1/2, and we'll deal with that one, plus 1/2 times our second value, x to the negative 1/2, and we'll deal with this one. So let's go ahead and apply our power rule. So we add 1 to our exponents, all over our new exponent. Add 1 to the exponent, all over our new exponent. And then I just add and multiply across. So this becomes 3 halves. So this is x to the 3 halves all over 3 halves plus 1/2 times, here it's actually only 1/2, so x to the 1/2 over 1/2. And now we can see visually I have a 1/2 and a 1/2, I can cross it out. If I didn't trust that, I could flip it and drag it to the front. If I flipped it and dragged it to the front, I would get 2 times 1/2, which again, just cancels out. I want to flip this and bring it to the front, so I want this to say 3 and this to be a 2. And I want to get rid of this x to the 3 halves, so that's going to be the square root of x cubed. So in the end, and this is going to be the square root of x. So in the end, I'm going to do it right here, 3 square root of x cubed over 2 plus the square root of x plus c. Always add that plus c. If I want to double check my work, it's right there. I did make a mistake. I'm really sorry about that. I was supposed to flip this and drag to the front. I didn't actually flip it. I made a mental error there. My apologies. So this becomes 3 and this becomes 2. So this should have been 2 and this should have been 3. Okay, so this is why these kinds of algebra mistakes are pretty rampant. It's pretty common. That's why I say you guys don't suffer in the calculus. You guys only suffer in a little bit of algebraic manipulation. As you can see, even I can make that mistake. So, next thing, we're going to do another algebraic manipulation. So first things first, we're going to get rid of our root. So that's actually x to the 1/3. And then we're just going to simply distribute across. So this becomes the integral of, I don't know why I was going to put 1/3 at the front. That doesn't help us. X to the 1/3 times x to the, technically the exponent is 1, minus 4 dx, which is the same as saying the integral. Again, I'm distributing. So 1/3 plus 3 over 3 gives me x to the 4/3 minus 4x to the 1/3 dx. And here I'm just going to do one big formula. So we're going to leave myself some space. Okay, so let's apply our power rule. Step 1, add 1 to my exponent, divide the whole thing by my new exponent. Step 1 and step 2. Now I simply combine, multiply, do whatever I need to. So this becomes 7/3, x to the 7/3 over 7/3 minus 4x to the 4/3 over 4/3. Again, I want to flip these and deal with that. So that becomes 3 over 7. And this becomes 3 over 4. I can see my 4's are going to cancel out. And then we want to deal with this exponent up here. So this left one's going to be 3 cubed root of x to the 7th over 7 minus 3 cubed root of x to the 4th plus c. If I want to double check my work, which is a smart thing to do so we can catch any mistakes, and that is the correct answer. So yes. Okay. Moving on, we have example 9. We're going to do, again, a distribution. This one's pretty simple, so we're going to do x times 2 becomes 2x, x times x to the 5th becomes x to the 6th, dx. And then we're going to go ahead and integrate that. So let's do 2x plus x to the 6th. Step 1, add 1 to my numerator. So this actually becomes, my exponent, 1 plus 1 over 1 plus 1 plus 1 over 6 plus 1. This becomes 2x squared over 2. The 2's are going to cancel. Plus x to the 7th over 7. And this becomes x squared plus x to the 7th over 7 plus c. We cannot forget our plus c. And if we double check our work, that is absolutely correct. And our final example today is going to be the indefinite integral of y squared times the square root of y. So here we have to do another algebra manipulation where we are going to change our root to y to the 1/2, and then we're going to multiply our exponents. So that becomes the integral of y squared times y to the 1/2. If I add these values, that becomes 2 plus 1/2, which is 2.5, which in my proper fraction mode becomes 5/2. So we're going to do the integral of y to the 5/2. I'm going to go ahead and apply my power rule. So step 1 plus 1 all over my new exponent, which is step 2. This becomes y to the 7/2 over 7/2, which becomes 2 to the 7/2 over 7, which is 2 square root of y to the 7 over 7 plus c, always plus c. And can double check, answer is correct. So that's all there is for today. Unit 7.1, it is just the power rule steps of integration.